All right, so let's get into an introduction of a very important topic in chemistry called chemical potential energy and what that is. And we're going to relate it to a common, say, example from physics. We know what gravitational potential energy is, and we're going to see how they're very closely related. Before we do that, let's remind us what we have already looked at one type of energy in chemistry, and that is the energy of motion of molecules. Right? We know that within this beaker, even if it was standing still water, we know that at the particle level, there's all kinds of energy of motion, right? Because, so let's just draw that as a quick review. And if that's a cold gas, right? I'm showing a gas, cold gas, so it's moving around, but it doesn't have that much, not moving that fast. And then, of course, say what happens when I raise temperature. Of course, we all know this is very intuitive. When I raise the temperature, what changes about the particles, about their motion, is they speed up. So hot. I would show longer arrows, meaning they're moving faster. Right? And I could do the same with liquid. If that's a cold liquid, then a hot liquid would be, I should also show a little bit of opening up of gaps in there. But especially, I'm just going to show much longer arrows, right? So cold and hot. So as temperature increases for solids, liquids, or gases, the motion, in solids it's a vibrational motion, the motion of the molecules increases with temperature, the velocity. And so we have that energy of motion. Energy of motion we give that, of course, the term kinetic energy. And the energy of motion depends on two things. And it depends on the mass and the speed or the velocity of whatever we're looking at. So, on the grand scale, of course, it's some big object that has some mass and some velocity. In chemistry, it's these small particles which do have mass, and there's a lot of them, and so there's all this energy of motion. So that is energy of motion. Now let's get into potential energy, and we're going to do that first with an example from physics, a roller coaster. So let's look at this example from physics, a roller coaster, and something we're kind of familiar with and can picture easier. And then we'll look at potential energy from chemistry. But this kind of thing, so let's take this roller coaster. Let's assume something, either a bigger hill or something, got it moving fairly fast. So down here, and we're going to call this a height of 0. Down here, this roller coaster has a lot of energy of motion. It's moving really fast. What happens as the roller coaster goes up the hill? It's overcoming gravity, and the gravity is going to slow it down. And so let's assume this hill was just high enough, to keep this simple, that at the very top it was actually stopped. It used up all of that energy of motion. We know that energy must be conserved. So what happened to the energy of motion? It became potential energy. And so you remember potential energy from earlier science classes. Gravitational potential, I'm just going to call it potential here. Gravitational energy depends on the location of an object with mass and the surface of the earth. If I take a wrench and I lift it up, I'm putting energy in to lift it. If I lift it up to here, I have changed its position. I put energy in. There's a certain stored energy to this arrangement, the wrench above the earth. I can use this energy to do something. I could drop it on a styrofoam cup and smash it, or something like that. So I've got some stored energy here that can be used. So here's the potential energy that this cart has gained. All of that energy of motion, if we ignore friction and things like that, all of the energy of motion has been converted into potential. And then so potential is based on the arrangement. And I'll just write cart / earth. Right? The more that the cart is removed from the earth, the higher the potential, right? So it's based on that arrangement, nothing about its motion now. So it's just potential, it's stored there. What can I do with this stored energy that it has up here on the hill? I can use it to get the cart going fast again. So I have energy of motion converted to potential energy, converted to energy of motion again, right? And so let's just write KE equals 1/2 mv squared. That's our energy of motion equation. So energy of motion, potential energy, energy of motion, and they're converting or they're transferring. So energy is conserved the whole way. It's just being converted from one type of energy to another. In chemistry, we have these same kinds of transfers that are directly analogous to this. So we're going to have a situation where energy of motion of particles, or thermal energy, that energy of motion, is going to be converted into chemical potential energy. And sometimes chemical potential energy is going to be converted into the energy of motion of molecules. So we're going to get these same conversions happening. So let's now picture it in the chemistry example. Let's take this and we're going to keep relating it back and forth from this example to the chemistry example. Okay, so in physics, when we talk about removing something or extending it to a farther away from the surface of the earth, and that's raising potential, now let's look at chemical potential energy. So it's also based on the arrangement, in this case, of particles in a system. So the chemical potential energy is not based on the motion, it's based on how are they arranged. When I go from solid to liquid to gas, particles are arranged differently. In solid, they're arranged in this kind of array and they're all attached together. Liquid, they're more random, they're moving around, but they're still in contact. And then gas, they're completely separate. I haven't put the arrows, of course, solids are doing this vibration. I haven't put the arrows on yet. So let's look at this from a purely based on the arrangement. When I do something, and we're going to answer this question. When I add ice to water, the water gets cold. And we say, well, of course, the ice is cold, but that's not the main reason that ice makes water cold. The arrangement of those solid water particles is going to change from solid water, ice, to liquid water. That change in the arrangement of the particles is going to be the main reason that adding ice to water makes the water cold, because it melts. So let's see why. So when I go from solid to liquid, that process, of course, is called melting. What is actually occurring during melting? I've got these solid particles and there is a force that's holding them together. If it's water, it's hydrogen bonding. But there's something holding them together. There's an attractive force between them. Otherwise, they wouldn't ever be solids, right? Something is attracting water molecule to water molecule. So, what is melting? What is melting? I am breaking attractions, right? So those attractions, because they were locked together, they're now moving about more freely. So I had to break those attractions, those attractive forces that were holding them in place. If you imagine, it's just like magnetism, two magnets stuck together, and you rip them apart like that. Breaking attraction requires energy, right? So it took energy to do that. Energy must be conserved. That's one of the basic properties of the universe, that energy must be conserved. So if I put energy into breaking those attractions, and I haven't did it without changing the temperature or anything like that, that energy has to be stored in this arrangement, right? Just like putting energy into lifting this wrench. I put energy in to get it up there. So if I put energy into lifting this wrench, that energy is stored in this arrangement, the higher position of the wrench. Therefore, if I put energy in to turn solid into liquid, that energy is stored, potential energy. So chemical potential energy is based on the arrangement of particles in the system. If I change their arrangement from solid to liquid, and changing that arrangement involves breaking attractions, then that new arrangement has a higher stored energy, which I can use. And then, of course, what happens next? Evaporation. So I wrote it kind of vertically like this because this is like our roller coaster. What's happening as we go here, lower potential, highest potential. We're not going to look at plasma, right? So evaporation, I am breaking attractions, this time just completely separating them into a gas. If it's water, this becomes water vapor or steam, right? So this has a higher potential energy. I'm just going to abbreviate potential energy, PE. Right? This has a higher potential energy. The gas has a higher potential than liquid, than solid. And we can see why, because if I have to break attractions, I have to put energy in to go from solid to liquid, then that energy is stored as potential. If I have to put energy in to go from liquid to gas, that energy is stored as potential. And so we can see that. How do I do that? Where does this energy come from? If I'm increasing potential, where is that energy coming from? Where is the energy coming from to break attractions? It's coming from the surrounding molecules. The surrounding molecules, like in my ice water, where is the energy coming from to break the ice? It's coming from the water around it. And it's very much like our roller coaster. In our roller coaster example, it was using energy of motion to gain potential energy. The same thing is happening here. Breaking those attractions requires energy. Where did the energy come? To raise the potential, it came from the surrounding molecules. In our next video, we're going to break down those examples of the ice and the water and some others where we get these transfers of energy from energy of motion to potential, or from potential to energy of motion.